Okay, so today we're going to be talking about topology. And topology has to do with open and closed sets, which we defined in the previous video. However, we define those concepts in terms of a metric. And there's a kind of more general definition. And the area of math that studies that more general definition is called general or point set topology. Okay, to recap, let me start with a case of a metric space. We said that a subset of X is open if for any element of A, there exists a positive delta such that X is contained in this bubble or this ball of radius delta around, X is contained in this ball of radius delta around X itself, which is contained in A, right? Where we recall that the open ball this is a set of all X prime and X such that the distance to X prime is less than delta, strictly less. A subset is closed if its complement is open. So this defines, well, that this says that certain subsets of X are closed, certain subsets are open, some are neither open or closed. So there's this collection of subsets that we're going to call tau of X, d sub X. And this collection is, what is this? All open subsets A of X. And it turns out that this collection has certain properties. And the properties that this collection has are, by definition, the properties of a topology. So what is a topology over a set, right? So, okay, what I want to do right now is that for a second, I want you to forget everything that I wrote. And I just want to say that basically, even if you don't have a metric, you can define a general topology over a set X. So suppose I give you an unempty set X. A topology over X is a collection of subsets of X, which I'll call open sets. That's just a name that I give to them. Well, saying that a subset of X is open, just saying it belongs to the topology, belongs to this big tau here. And the defining properties of a topology are the three properties I have over here. First of all, the empty set is open, meaning it belongs to tau. The whole set X is open, so it belongs to tau. Second property is that if I have two open sets, their intersection is also open. So if A1, A2 belong to tau, the intersection of A1 and A2 also belongs to tau. And you can easily check for induction that if this is true of two sets, it's true of any finite number of sets. So if A1, A2 up to En are open, it means that the intersection of A1, A2 up to En is also open. Right? You can prove that by induction, say. Okay, but this is property number two. The third property is this. So take any collection of subsets of tau, any collection of subsets of X contained in tau. So take any collection of subsets of X, which are all open, right? So which all belong to tau. Then if I take this union of open sets, this union is also going to be open. So we summarize this by saying that the empty set is open, X is open, intersection of finite number of open sets is open, union of any number of open sets, countable, uncountable, you name it, is also open. Okay, so as we're going to see, there are certain concepts which we'll call topological that you can define simply in terms of the structure of open sets. And by the way, if a set is not open, but its complement is open, we call it closed, right? We know that matches what we saw in the case of metric spaces, so that sounds appropriate. But we're gonna see that many things can be defined just in terms of this structure of a topology. But first of all, what I want to check is that this notion of open set agrees with what I described for metric spaces. So here's a proposition. I have metric space I define this tau, like before, tau of x d sub x is a collection of all subsets of x that open according to d sub x. And then tau x dx sub x is a topology, so it satisfies this definition. Now, this proposition seems to say that there's nothing to the concept of topology because that it's only something that we derive from the notion of metric. However, it's easy to check that there are topologies that are not given by any metric, and just here's one silly example. The chorus topology. It's a topology, well, it's a collection of subsets of X, so I have to define it. And I just say, well, only the empty set in X are open. Everything else is not open. There's also the fine topology, which is all subsets. And it's easy to check that on the one hand, this topology does not come from any metric. And I mean, if we're in a more advanced class talking about general topology, we'd see that there are actually natural topologies out there, topologies that are useful for analysis or for other areas of math, algebraic geometry, and etc. They're not given by metrics. So this is not like such an exceptional, silly case after all. On the other hand, this is also a topology just because, well, the family of all subsets of X is closed under intersection, under union. Empty set and X are subsets of X. So this is a topology, and this one is given by a metric in this sense. But I'll leave it as an exercise for you to determine which metric gives this topology, right? For the time being, what we want to do is just to show that given any metric, you have a natural topology associated with it. The remark says that it's not always the case that given a topology, I have a metric that gives this topology. Okay, so in order to prove that something is topology, we have to prove that it satisfies these properties, right? So clearly this tau x dx d sub x is a family of subsets of X. This first property is obvious and we checked it in last class, right? So we know that the empty set is open according to the definition that we saw in the previous time. X is also open. Next step is to prove that given two open sets according to this definition, their intersection is also open. Okay, now what we have to do to prove that a set is open? We according to the metric, right? So what we have to do is that we have to check that condition of the protective bubble, right? Given a certain X belonging to the intersection, I need to find a positive radius such that the ball around X of that radius is entirely contained in the intersection. What do we have? We have that A1 is open and X belongs to A1, right? Okay, so it has its protective bubble inside A1. So we call this R1. And the same thing for A2. So since A2 is open, X has its little protective bubble inside A2. Now I need a protective bubble that works for the intersection, right? And that's easy. I just take delta to be the minimum of R1 on R2. Therefore, Bx delta, well, since delta is less or equal to R1, we know that this ball is contained in A1. We know also that this ball is contained in A2. Therefore, the ball is contained in the intersection. So, no big deal, right? So, Okay, so what do we have now? So, okay, given x belonging to the intersection, we found a positive delta, right? This is the minimum of positive numbers, so it's positive, such that b of x delta is contained in the intersection. Okay, that's great. So that holds for an arbitrary x in the intersection, therefore the intersection is open. So we're done with property 2 here. Now 3 is in some sense easier, even though it's kind of a fancier statement, right? It has this union that could be uncountable. But let's look at it. So we're given our family, our collection of open sets, and we want to prove that this union is also open. Sorry, A belonging to the family script A, and this is tau x d sub x. How do we prove that? Okay, again, we have to take an x that belongs to the union, and we have to find it a protective bubble. If I have positive radius delta such that bx delta is contained in the union. Well, what do we know? We know that if x belongs to the union, there exists a subset in this union that x belongs to, right? By definition, the elements of this union are precisely the guys that are an element of at least one of these sets. So let's take one of them. Now, because this is a collection of open sets, it must be that there exists a delta such that we have this protective bubble around x that's entirely contained in a sub x. But now we're done, right? Because a sub x is contained in the union of all these sets, right? So this is a union. A sub x is one of the sets in the union. So the union contains a sub x, which contains the bubble. Therefore, the bubble is entirely contained in union, right? So we give an x, we found it a bubble that is contained in union. So the union of open sets is open if we define opening according to a metric. So now we have everything that we needed, right? So we saw that the specific topology generated by open sets according to the metric d sub x is indeed a topology according to this general definition. So there's no contradiction between the two things, even though, as I mentioned, there are topologies that do not come from a metric. Okay. Now, as I mentioned, we have this concept of closed sets. Well, what is a closed set in a metric space? Is a complement of an open set according to the metric. What is a closed set in a general topology? Is a complement of an open set, a set in the topology. So again, there's no contradiction. And but it turns out that as a consequence of these properties, I can prove that if f1 and f2 and x are closed, what does it mean to say closed? It means that x minus fi belongs to the topology. Well, in this case, this specific topology, but it could be a general topology. If I have two closed sets, then their union is also closed. And how do I prove that? Okay, I'm using this symbol here for the complement of a set F, right? So it's everything that's in X but not in F. So let me use a more standard notation, Fi complement. But except that when I use this complement here, I need to make sure that you understand that there's an implicit universe here, right? I'm taking the complement of F1 and F2 with respect to this universe X, where they're both contained. Okay, right, so I want to prove that this guy is also closed, which means that the complement of F1 and F2 should belong to the topology, right? And is this true? I claim it is, and it's actually contained there. And this is going to be one first instance where we prove things just by using, well, properties called I forget, the Morgan's laws of set operations, right? We already used some things about saying, well, a union contains, if a point belongs to the union, if and only if it belongs to one of these sets. Now we're going to use things that are slightly more sophisticated. So, and one of them is here, is that if I take a union of sets, and I take its complement, which I want to analyze here. Sorry, this U. So the complement of a union is the intersection of the complements. Okay, how is this useful? Well, by assumption, these guys are both open. So by axiom 2 of a topology, this guy also has to be open. So there's implication going here. Open and open gives open here. But then if this is open, if this FU union F2, F1 union F2 complement is open, then the complement of this set is open. And what is the complement of a complement? Sorry, the complement, if this is open, its complement is closed. So F1 union F2 complement is closed. But what is this? It's just the union of F1 and F2. Okay, now what? Well, I mean, it's sort of, what have you used here? I have used two things. Again, it's this thing that complement of a union is an intersection of complements. You can check that. It's pretty obvious once you think about it. The other thing is that the complement of a complement is the set itself, right? So I'm looking at everything that's outside the set. So, okay. So now we know, just from the fact that, that in any topology, a union of two closed sets is also closed. That holds for a union of a finite number of closed sets, because an intersection of a finite number of open sets is open. Now, what's the equivalent of this property, right? That here I'm saying arbitrary unions of open sets are open. So arbitrary intersections of closed sets should be closed. And let's check that. If F is a collection sets, it means that the intersection of these guys is also closed. And why is that? I mean, I'm going to be sort of quick, but if you want to check that something is closed, what you have to check is that the complement is open. As we notice, the complement of a union is the intersection of complements, and you have also the opposite property, right? The complement of an intersection is a union of guys. These guys are all open. This union is not exactly this form. I mean, here I have a union of all the elements of script A. Here I have the union of the complements of the set script A. But I could write this down as this, where A consists of the complements of the set in F. So it's a different collection. And therefore, if I have a union of open sets, the whole union is open. Meaning that this guy here, its complement is an open set, therefore it must be closed. Okay? So, yeah, so kind of the dual properties here are, if the intersections of finitely many open sets are open, then unions of finitely many closed sets are closed. If unions of however many open sets are open, then intersections of however many closed sets are closed. And also we have this property here, which I forgot, right? So if this guy is open, its complement, which is empty set, is closed, and vice versa. This we showed for metric spaces last class, but it also follows from these general things. Okay? So now I want to sort of switch gears, and I want to define a few topological concepts just in terms of a topology, right? So by the way, if you have a pair where X is a set and tau is a topology over X, that is by definition a topological space. And to repeat, general topology is the study of general topological spaces. There's surprisingly a lot of stuff that can be said about this concept. It's important in logic and set theory. There are all sorts of questions in logic that are related to general topology. So we're going to be spending basically a few minutes, or the few remaining minutes of this video, talking about general topology. And in the next video, we're going to be switching back to metric space topology just by showing how the concepts I'm going to define right now appear in the metric setting. Okay? Remember, by definition, a closed set is the complement of an open set. However, for metric spaces, we know that a set is closed if and only if, for any sequence contained in that set, that converges, the limit is also in that set, right? We showed that in the previous video. So now, we're going to be defining some concepts purely in terms of topology, and then we're going to show that they have metric descriptions. Okay. Let me define these notions. So I'm going to take a topological space, again, just a set, non-empty with a topology, and I take an arbitrary subset of X, and I'm going to define a series of guys. So this is the interior of S, and it's a big union of open sets. It's sometimes called the largest open set contained in S. How is that? Well, first of all, notice that this interior by definition is open because well, it's a union of open sets, right? Now, any open set that's contained in S must be one of the sets in this union, so it's contained in this S ball over here. So the interior is the largest open set. So yeah, due to some technical difficulties, I had to switch headsets. So, okay. Interior of S is the union of all open sets contained in S, therefore it's open. And it's the largest open set contained in S because any open set contained in S must be in this union, therefore it's contained in the union. There's also the closure of S, and the closure, I'm not going to write closure of S, I'm just going to say the closure. It's the intersection of all closed sets, and I mean closed sets in terms of the topology over here, and now I have to reverse, and I have the intersection of all closed sets that contain S. So this is the smallest closed set that contains S, meaning it's a closed set because it's an intersection of closed sets. And any closed set that contains S, it appears in the intersection, therefore it contains the intersection. Right? Okay, so one more thing. For the time being, there will be another one in a couple of minutes. The boundary of S is by definition the intersection of S with, well, the intersection of the closure of S with the closure of the complement of S. Okay, this is all very abstract, right? So let me first of all observe that we have noticed that this is open. The interior is always open. The closure is always closed. This guy is the intersection of two closed sets, therefore it's also closed. But clearly there should be a lot more we can say about this because, well, you know, these are supposed to be important concepts, right? Otherwise I wouldn't be talking about them. So let me start with the interior, right? So I've been talking about these protective bubbles or protective balls around points, right? So let's say that any open set X, if X belongs to an A open, A is contained in S, I'm going to say that when this happens, X is protected from the stereo of S, or protected from the complement of S. And in that case, the interior is precisely the collection of points. They're protected from the outside of S. Meaning, for each point in the interior, there's an open set that it belongs to, and this open set is entirely contained in S. Right? And that's the definition of the interior, because that's the union I have over there. Okay, so this is sort of, okay, not too hard. So the interior, the points are kind of far away from the outside of S, or something like that. When we talk about metrics, it's going to be clearer that, this iteration will make even more sense. Okay, what about the closure, right? So let me write it again. The intersection of all closed sets that contain F. So the closure is more or less the opposite. A point belongs to the closure if and only if it cannot be protected from S. Meaning, proposition, a point X belongs to the closure, right? X is, of course, a point in my universe set in X. Little x belongs to the closure if and only if for any open set containing X, the intersection of A and S is non-empty. So there's no way to find a protective bubble for X contained in the complement of S. Any bubble, anything that you try to build to protect X has to intersect S. In this sense, X is not protected from the outside, from S. Okay, how do we prove this? I'm going to prove, as usual, proving each direction at a time. So suppose that X, let's assume to get a contradiction, X belongs to S bar, but there exists an open set A, open, with A belonging to X, but is already here, and A intersection S equals empty set. So what does that mean in the picture? I have S here. I have this open set. I have X, and I have this open set A containing X that does not intersect S. I claim that in this case, there's a contradiction because X does not belong to the closure. And how is that? Okay, A is the set here, right? So let me move this inside. What about the complement of A? It's closed. Notice, if A doesn't intersect S, then the complement of A must contain S. It's sort of easy to see that in words. A and S have no points in common. Therefore, all points of S do not belong to A. They belong to the complement of A. Therefore, all points in S belong to F. So, right? F is closed. F contains S. And as we notice, the closure is the smallest closed set containing S. Therefore, F must contain an S bar. Well, must contain S bar. If you don't like this explanation, say, well, if F is a closed set that contains S, then it's one of the sets in this intersection, and therefore it contains the intersection. Okay, so what are we saying here? That's the same. Remember that F is a complement. So we're saying that A intersection S bar is the empty set. But, or however, we assumed that X belongs to A and X belongs to the S bar, right? So we started out by saying, assume X belongs to S bar and that there exists an open set, blah, blah. So X is an element that belongs to both A and S bar. Therefore, this intersection is non-empty and we have a contradiction. It cannot be that X belongs to S bar and there exists an open set that X belongs to that does not intersect S. Therefore, if X belongs to S bar, it must be that any open set containing X must intersect S. So that's one direction of our thing. Now what about the other direction? So assume that a point X satisfies this property, right? Assume, and let me call this for the time being so that I don't have to write it again. Assume star, but X does not belong to the closure, right? What does that mean? Well, if X does not belong to the closure, it does not belong to an intersection. How does a point get to not belong to an intersection? Well, it must be that one of the sets in the intersection does not contain X, right? On the other, to put it in contrapositive form, if all closed sets containing S containing X, then X belongs to the intersection. Okay, but there's this closed set, right? So what about this? Okay, so look at A, which is F complement again, right? So everything we know in general topology about open and closed sets is that the complement of open is closed and vice versa, and they're kind of axiomatic properties. So F complement is open, X belongs to A, and therefore by property star, right? Why does X belong to A? Because X is not an F, therefore it's in the complement of F. If X belongs to A, then by star we have that A intersection S is non-empty, therefore F complement intersection S is non-empty. But this is a contradiction again, right? Because we are assuming F contains S. So let me go back to my previous drawing. So we have F over here. This A is the rest of the world, right? So F contains S. X is over here. And but how can it be that the complement of F contains S2, intersects S2? Well, if F contains S, no element of S is in the complement of F. And therefore we have yet another contradiction. And we're done, right? So again, what is the contradiction we found? If we assume star, then it must be that X belongs to S bar. Otherwise we have a contradiction. That means we're done, because now we show that this implies this, already had the other direction. Okay, so now we know what the elements of the closure are. The guys such that if you take any open set that they belong to, this set is going to intersect S. Okay. Well, okay, just as if you're curious about why I keep walking to the computer and sticking my finger in it, it's decided that it wants to sleep, like maybe some of you. But like my computer, you should resist that urge. And if I could, I'd go and poke you to keep you awake, but I can't. So you have to do it yourself. Okay, but right. So after this very weird diversion, let me observe that now we know that we know something about the closure. Remember that the boundary is an intersection of closures, right? So what is the boundary? The boundary is this guy. When does a point belong to the boundary? Well, by what we just proved, it must be that any open set containing that point intersects both S and S complement. So you can see why it's called a boundary, right? So let's say X is here, this is S, the other side is S complement. What we're saying is that, yeah, it really is like a boundary, right? So it's sort of saying any A that I take over here has to intersect both sides. Okay. Right, so there's a fourth topological notion, right? I talked about interior, closure, boundary. And now there's a fourth notion, which is related to what we just proved about the closure. So points in the closure, they're such, they're not protected from S, sorry, right? So for all A X open, A intersect S is non-empty. But let's say that there are more and less interesting way of this happening. Notice that what I wrote over here, right, is sort of, it's trivially true if X is itself an element of S, right? So assume X belongs to S. Well, now you know that any open set containing A contains this point little x. This point little x belongs to S, therefore this intersection is non-empty. So what we're going to look at now is a notion where the sort of dumb non-empty intersection is excluded on purpose. So we're going to say, okay, and for that I need a slightly longer definition. And I'm going to say that S is an accumulation point for S if for all open sets containing S. Again, whenever I say open, I'm talking about this set with this topology. So I want this intersection to be non-empty, even if I exclude point S. Right, so the difference is before I wanted any open set to intersect S, now I want any open set to intersect S minus this element, which may or may not be in there. Right, so, okay, so we reached this point where we define accumulation points, and the so-called derived set of S is simply the set of all accumulation points of X. We're gonna show that this set is closed, right? Remember that the closure is always closed, the boundary is always closed because it's intersection of closures. The interior is always open because it's the union of open sets. We're gonna show that this guy is closed too, but for that we need an additional assumption. An assumption about the topology. Assume that for all X in X, the unitary set containing X is closed. Remember that we saw one example today of a topology that just had its sets, empty set and X. Those are the only open sets. So in such topologies, this may not be true, right? If capital X has more than one element, then this is not going to be true. But assume that your topology has this property. They're all unitary sets are closed. Then S prime is closed. How do we prove that? Well, it's a bit tricky, but not too tricky. We need to use this property. I mean, this is topological spaces satisfying this are called T1 spaces. They're the first class of spaces in a hierarchy of topologies that satisfy more and more stringent properties. Luckily, all metric spaces have this property because this guy here is a closed ball radius 0, and we saw that all closed balls are closed. So for metric spaces, this assumption is clearly satisfied. How do we prove then with this assumption that S prime is closed? So, okay, I'm gonna prove it with a picture. Okay, so have S here. So what we're gonna do is to prove that the set, the complement of this set is open. Right? So to prove that something's closed, suffice to prove that the complement is open. So what's the complement? Well, okay. Here I have a point X. X belongs to the complement of the derived set if this does not hold for X, right? If I replace X with S here, this does not hold, so there must exist an open set depending on X. So I'm calling it A sub X just for convenience, open. And now I want to say that A sub X intersection S, well, here I have to remove the point and say the intersection is empty. But if I do that, I have two choices if I want to write it like this. So either this intersection without removing X is empty, or it's equal to the unit set X, right? And you can follow my logic. So there are two choices. If I know that this intersection is empty, then I know that A sub X intersection S minus X is empty. If I know this intersection is equal to X, then if I remove X, it is empty. And these are the only possible cases. So what I know about this guy, I don't know if it belongs to S or not, but I know it has this bubble around it where perhaps there's a single point of S in this bubble that will be precisely X. But maybe there's not. Maybe the two guys do not intersect. Okay, how do we go from here? So notice that the union of these, well, let me move this union somewhere else because I want it to be visible. The union of A sub X over all S, X is the complement of the derived set. This contains the complement of the derived set. What does that mean? It means take a point in here that's not in the derived set, right? In the complement of the derived set, it's containing one of those sets, A sub X, and therefore it's containing this union. So there's no question that the complement of the derived set is contained in the union. The union is open because it's a union of open sets. So what we're going to do now is to prove equality here. We're going to prove that the complement of the derived set is equal to this union. And that's what we need because in that case, we know that the complement of the derived set is open, it's a union of open sets. How do we prove that? So what we have to show is that any point in this union is also in the complement, is not a derived, is not an accumulation point, right? So, okay, so let me take a Z in the union. If a Z is in this union, it must be in one of the EA axes. So it's one of the sets like this. So we have this set that contains Z, right? So it's A sub X, contains X, and also contains Z. And we know that the intersection of A sub X with S is either empty or X. Now I'm going to define a set for Z, which is the open neighborhood we're looking for. I just take the same set as X, A sub X, and I remove X from it. So now this guy's gone. Right, so notice that this set does not intersect S necessarily, right? Okay, here I'm assuming that Z is different from X because I know that X is already a non-accumulation point, so I'm going to prove that any other Z in A sub X is a non-accumulation point. So I took Z, and I define a neighborhood of it, an open neighborhood, which is A sub X minus X. How do I know this is open? Well, my assumption is that the set containing X is closed, and A sub X minus X is the intersection of A sub X with the complement of the set. So it's the intersection of open with open, right? So this is the same thing as saying A sub X intersection unit X complement. So if Z is not X, this is an open set containing Z. This open set does not intersect S. Now, wait a minute, what did I just show? I showed that Z is contained in an open set that does not intersect S. Therefore, Z cannot be an accumulation point, right? So what we just showed is that any Z that's inside here that is not X is a non-accumulation point because you take this neighborhood, remove X from it, That's another open neighborhood. A neighborhood of a point is just an open set that contains it. So you take this neighborhood, remove x, that's still a neighborhood for this point, and this neighborhood does not intersect S. Therefore, any z in here that's not x is a non-accumulation point. X is a non-accumulation point by assumption. So it turns out that all elements of A sub x are accumulation points. That holds for all x. Therefore, any set in this union is a set of non-accumulation points. It's contained in the derived set, and the whole union is contained in the derived set. Therefore, the union is equal to the derived set. Notice that at a key step, we needed to remove a point from an open set and say that this set was still open. And that's where we use this property that we're assuming. That for all x, the unit set containing only x is closed. If we don't have that, then there are counterexamples where we showed where S prime maybe is not closed. But in our setting, as I said, this is always going to be true, so we don't need to worry about this. Okay, and with this, we've finished this discussion of general topology. We're going to now move to the metric setting and show that, the closure, the interior, the boundary, and the derived set can be defined in terms of just notions related to convergence of points or distances. So there's a correspondence, a more direct correspondence than what we showed here. Thank you.